Okay, guys, welcome to lecture number 15 on Physics 140 for this semester. And just to review a bit what we have been seeing in the last lecture, we saw exactly the process that gives rise to a laser, which is stimulated emission. We actually understood that to actually have a process as a stimulated emission, we have to somehow invert the natural population between the excited level and the ground state on a system. And those two states should be linked somehow by an optical transition, meaning an electron should transit from the excited state to the ground state by emitting a photon. And actually, if I have a large number of atoms in the system in the excited state, a photon with the right frequency can actually stimulate the decay between both, and this is the principle of how a laser works. So this has to do with the exact difference between the energy of an excited state and the ground state, and this is sort of the basis of almost all atomic transitions, essentially, in solid that has to do with the interaction with photons. There's another class of spectra, which is not a line spectra as one could expect by having discrete energy levels, as I am showing here in this case of what I call a toy model for a laser. But we can get an intensity as a function of wavelength that is expressed qualitatively in a shape like what I'm showing here. It means that there is a spectral distribution of intensity, which is particularly of each temperature. If I change the temperature of a solid, the emission of this intensity as a function of lambda will change. The total intensity as a function of nothing. The total intensity emitted from a solid at a certain temperature T can be calculated by doing this integral. And I'm going to ask you guys to actually do this integral as part of the homework this submitted for you today. And this integral, when it's done, is equal to a constant, which is called the Stefan-Boltzmann constant, times the temperature to the fourth power. Okay. So that's the way a solid loses heat at a certain temperature by emission of radiation. Some of the energy on the solid is carried away by the photons that leaves the subject or the body at a certain temperature, simply because it emits radiation in this way. This is a key thing in global warming, actually, because the sun is. I didn't say that last time. I'm going to mention it now. The sun emits radiation at a temperature that is comparable to 10 to the 5 times 10 to the 3 Kelvin, okay, and has a color and spectra center in the optical color about 5,000 angstroms, okay, and the wavelength of the light is about 5,000 angstroms, and then this can get through the atmosphere, get to the Earth, and it warms up the Earth. And when it warms up the Earth is traveling through space, and it will cool down by emitting radiation. What radiation emits? It emits infrared radiation with a law very similar to this, with the temperature of the surface is 300 K, which is the ambient temperature everywhere, and it's emitted a sizable amount of energy. And it is good that it does that, unless the thermal energy cannot leave the Earth. Why wouldn't it be able to leave the Earth? Simply because the atmosphere is not transparent to that radiation. And that's what happens with the emission of hydrocarbon in the atmosphere, the presence of CO2, for example. It's a gas that actually absorbs part of the energy and warms up the atoms in the atmosphere. And if the atmosphere is warmed up, the Earth is going to be warmed up. So the great discussion right now is that since due to the fossil fuels, the Earth is less transparent, the atmosphere is less transparent to the infrared radiation. That's where we're getting warming up, which could get to 1.5 degrees, which will be an enormous catastrophe. At the center of that is understanding this process. This is the physics that has to do with the global warming, actually. Okay. Well, apart from actually the absorption of this light emitted by the Earth by the CO2 molecules and other hydrocarbons and methane, for example, also in the air. Okay. Okay, let's go to the central part of this lecture today, and let's revisit a bit the wave-particle duality. Okay, and so this is an experiment that has to do with electron diffraction. Now we know that there is certain uncertainty in the particles because the particles can now behave as waves. And if they behave as waves, it means that it's possible to do an experiment where I could send in a wave of electrons and have two small slits, let them go through. And I find out that essentially the intensity of that experiment looks pretty much like the intensity of a photon going through the same type of slit. So it makes almost no difference if it is a wave or particles, because I said photons. Photon means electromagnetic radiation, and in the case of electromagnetic radiation, we use wave theory to calculate the intensity in the screen as something that looks like this, like the red line, And here now we're talking the intensity about particles, and what is the intensity of particle? It means the number of particles in each point. So how does this work? We have electrons that now behave as waves. So we associate with electron a wave picture like this. They have a characteristic wavelength. And if the condition is such, I could have an electron interacting actually with its own wave, because and I can do an experiment like this with very low flux, and do I have that somewhere? Here it is. And this is sort of the same experiment taken out of the book. So if I let go 28 electrons and look at the screen that I have here, this is a screen where I collect the electrons, and each white spot means an electron that have made an impact here, and I send them essentially one by one. And if I do that, if I send them with a very low flux, we get a spectrum that looks like this, and if we collect more electrons, it looks like this, and then more electrons, it looks like this. And at the end, this looks pretty much as the same interference spectra that you will get out of waves, calculated by waves. This is what we did before, okay? And if the flux is low enough, it's not that this electron will interfere with this electron. If the flux is very low and I'm sending the electrons one by one, I also get the same pattern. So it means that this electron somehow has a probability of going through this slit and a probability of going through this slit. And actually the interference that we see is the wave associated with this single electron is interfering with itself. Half of it is going through here and half of it is going, not half, a fraction is going through here and a half fraction is going to there. Otherwise, I cannot explain why I get a pattern like this, okay, at a very low flux. So this is a very interesting aspect of electron interference. So this is a feature that is very relevant. We cannot identify the slit in which the particular electron went through. It means that the other thing is that, you know, one electron wave packet can interfere with itself while going through the both slits. So a fraction of the electron goes through one slit and goes through the other. You cannot actually determine over which slits the electron goes. This is a new thing, okay? This is the difference from regular mechanics. Uncertainty principle. So we discussed this before. So we have all particles present an uncertainty in momentum of the form delta px times delta x, delta by times delta y, and delta bc times delta z is greater than or equal than h bar over 2. Okay, so this is somehow linked to the fact that particles can be represented as waves. So essentially, if I have a particle that is represented by a wave like this with a region of space where the particle is actually significant, the wave associated with it is significant, it means that for having this type of wave with the particle confined or locatable in a certain region of space, it means that I need a region of a section of momentum. So a particle cannot have a definite momentum if it actually can be located in a region space. So this is very sort of significant. This is Heisenberg uncertainty principle. In addition, quantum mechanical systems exhibit also an uncertainty principle linked to energy. Okay, so the precision of the precision of the energy of a particular state and the time that that particular state lives also have an uncertainty principle exactly linked to very similar to this. So delta E times delta T is greater or equal than h over 2. This is also has to do with the wave nature of the particles involved. So the illustration is as this. So we have atomic levels that has certain width, means instead of being a line, very narrow line or a state with a very well-defined energy, we have a state with that can actually have a range of energies here. And all of this particular state here, all this energy range, this energy range is possible for this state. So it means that in this case, it means that delta E is large. So if delta E is large, it means that this state is short-lived, because the precision of time that it can have here, if the delta E is too large, the delta T must be short, okay? And in this particular case, when we have a very narrow line defining the energy of a state, this means that the time, this particular state is going to live a long time, okay? So when we were looking at this type of processes, we were describing that the type of transition that you need this state to be long-lived, the excited state in a laser, in order for the laser to work. And the additional state, the higher excited state should be a short-lived state. So at a certain time, that would allow the inversion of the population and having a large number of atoms in this particular excited state. The difference in these two states means that the width of each of those states is different. So there's also this is tricky, you have to understand this feature exists it's different from this one, and I recommend reading a bit more of what I'm saying here. I'm not going to be using this too often during this semester. I would like you guys to understand this a lot better. Okay, so but you know, reading about the uncertainty in energy is quite an interesting thing. Here I have an example. I don't want to go into the details, but you know, essentially, if you have an energy, you know, if you have a lifetime of, let's say, 1.2 times 10 to the minus 8, which is the characteristic line width or lifetime of state that is used for generating a laser. You know, that implies a width of the line associated with that state. And if you do the calculation, it turns out that this is only 0.02 micro electron volts, which is a very narrow line. Okay, a very narrow line. It means, well, I don't know how narrow it is. Well, it is small, but it is. It represents a lifetimes of 1.2 times 10 to the minus 8. So this is the restriction associated with the lifetime of a state, given the uncertainty principle in energy. Another aspect that is relevant to consider is that, let's say we want to confine a particle, and let's consider that particle to be an electron, in a box that is sort of, you know, the size of an atom. Okay, I changed the length here to be 0.5 at the end, but let's consider the size of an atom, essentially. So the box, if the electron lives inside this box, it doesn't have a potential in there. It's a flat potential. So it can move inside the box here with an energy as it was a free particle. So it could have a well-defined momentum and going in this direction, and a well-defined momentum going back, because it will bounce from the box here and there, going back and forth. Okay, and so just by the fact that we are confining this particle, we are forcing this particle to move. So this is something strange, because this has to do with the uncertainty principle, because I cannot have a particle fixed in space with zero velocity. And because that will violate the principle, because if it's zero velocity, it means that the delta P will be zero, so the delta X could be infinity, so I don't know where the particle is. But now if I put a box and I put the particle inside the box, there's a restriction here. There's a minimum kinetic energy that this particle can have while living inside here, okay? And that minimum kinetic energy has to do with the fact that it cannot be standing still inside the box, because if it's standing still inside the box, it will mean that delta P is equal to 0. So it will mean that delta X should be very large, but we know that delta X is not very large because it's located within the box. So there's a contradiction there. How do we solve that? Well, the particle cannot be at rest if it is confined to a small volume, as I'm showing here. How does it work? Well, delta Px times delta X should be greater or of the order of h bar over 2. If that's the case, the delta Px will be the range of momenta that it could have. So if it goes in that direction is P, and if it goes in the other direction is P also, but in the other direction, so delta Px is essentially twice P, okay? If delta is twice P and this length here, delta X is the length. So, and I'm considering that of the order of h bar over 2. it means that the momentum is h bar over 4L, and I can calculate the kinetic energy of the particle moving inside, and it turns out to be of the order of 1 electron volt. You know, so if I have a particle, I change the size of the particle here of the box, since I made it equal to the Bohr radius to have a reasonable scale, and if that were the case, the energy that the minimum energy that the particle can have is of the order of 1 electron volt. This value compares very well with the energy of an electron in a hydrogen atom. The energy of an electron in a hydrogen atom is of the order of 13.6 electron volts. So it's a factor of 10. Well, you know, it's a factor of 10 because this is a very rough calculation. I'm not going into the details of how it happens, but the fact that you could, you know, if you try to confine a particle to a region, that essentially gives the particle certain kinetic energy in order to actually comply with the uncertainty principle, you know. So uncertainty induces motion. Okay, this is something that it's in the back of this arrangement. So here I have the homework that I mentioned to you before. You guys should try to work this out, find out how the intensity, if you can actually calculate the intensity of emitted radiation as a constant times t to the fourth, beginning from the Planck radiation law, and you can use this as a hint for doing the integral. Okay, I'm sure you can do the integral by yourself, but you know, use this in order to simplify your calculus. So quantum mechanics. With all the evidence we have, you know, if you do something like what would that be? Nothing. If you want to look at the motion of a particle or a macroscopic object, you use Newton's law, you know, F equals ma. So we need to come up with something similar in order to describe the microscopic world that occurs at the level of atoms, for electrons and atoms. The way the word that was sort of coined for that was this is a new mechanics. It's a quantum mechanics. It's it should so whatever we were doing before with Newtonian mechanics is not a good model to represent electrons in an atom. We have to verify that they somehow follow or somehow comply with the uncertainty principle, because there's evidence that they do that. So essentially, the electrons should behave somehow as waves. They should diffract. They have associated with them a wavelength, and whatever equation of motion we have for this system, it's probably not going to be an equation of motion like Newton's law, but it will be more like a wave equation. So the mechanics for particles in a small dimension should be described by a wave equation, and that's why I would like to review a bit the wave equation in one dimension. And this is what expression 1 here shows. This is we can think of this as a perturbation on a string. Okay, so we have a string in the x direction. Okay, here this is one dimension in the x direction, and y would be the deflection in the y direction, the amplitude of the deformation of the string, which is supposed to be very small in every point. V would be the velocity of sound, the velocity of the waves along the string. This is what it is. And the equation of motion that actually rules this is something like this. The second derivative, and we can, you know, I'm sure you have done this in the past. You can obtain an expression like this by exactly doing Newton's law in a section of the string. Okay, and this velocity has to do with the tension and the density and whatnot. Okay, so you can get to this equation of motion in base of Newtonian mechanics, but now I would like to revisit this and understand a few features. For example, this here is y, which is a length, okay, divided by twice a length. So it's a length divided by twice a length. So this is the left side of the equation. The right side of the equation should be the same. I have a length up here divided by, you know, by v squared times delta t squared. This is also a length, because that is what it defines, that this constant over here, that's why it's written this way and not on top, because this constant must have a dimension of velocity for this whole equation to have the right dimension, meaning this side is length divided by length squared, this side should be length divided by length squared, and that happens only if v squared has dimensions of velocity squared. Okay, that's what it is. Okay, so the solution to that equation in general is they are, you know, these things are harmonic, because you have a second derivative here and a second derivative here, and the second derivative here should be to one variable should be equal with a factor in front to the second derivative of the other one to the variable of time. So it can be proved very easily that this is sort of a reasonable solution, which is why it's the perturbation is equal to the amplitude time a cosine minus an amplitude time a sine. Okay. Another way of representing this is this way that I have here, which is the exponential form of this, where well, the actual perturbation, it should be real. So at the end, I should take the real part of whatever this leads me to. Okay, so this way of representing the perturbations is the same as this one, with the only restriction that I should take the real part of this. The A twiddle and the B twiddle here are somehow related to the angle phi that you have here, and A and B somehow should be defined by the boundary conditions in the system. So I take this to be the valid perturbation. I replace it. This is the same as what we did before with the, and I replace it here. Take the second derivative with respect to space, and take the second derivative with respect to time and divide it by v. That's what I did here. The second derivative with respect to space is ik squared, is equal to the second derivative with respect to time is iw squared divided by v squared. Why? Well, you have to be reminded that the derivative of an exponential is the same exponential again, you know, times the derivative of the argument here on top, you know. So that's what I'm simply doing, and I have canceled in both sides here this factor a. So this is ik squared times y is equal to minus I omega squared divided by b squared times I. I cancel the I here and cancel the I there, so I have this expression. And this expression, what gives me is our familiar relation between the wave vector, which is associated with this solution here, the velocity of propagation, and the frequency. Okay, so So if the velocity of propagation is something determined by the system, which it usually is, in the case of light, is the velocity of light. In the case of a perturbation, like in a string, as we're seeing here, this is the velocity of sound, and this is the wave number associated with this wave, with the solution to this equation. So K is equal to 2 pi divided by lambda. This is the way it is defined, because when I change this factor here by a value of lambda, the argument here changes in 2 pi. So this is called a wavelength. So that's why K times lambda is equal to 2 pi. So this is the definition. This is the wavelength of the wave. So another way of writing it is this is periodic in space with this periodicity, with the periodicity equal to lambda, and it's equally periodic in space with the periodicity equal to 2 pi over t. T is the period if I stand in one point and look at the perturbation oscillating, the perturbation will oscillate with a period equal to t, going up and down. Okay, and v times t, the velocity times the time, is equal to lambda. This we can get v times t equal to lambda from this expression, because here we have 2 pi divided by lambda, and here we have 2 pi divided by t. Okay, from those two things, we define the period, and we can find that the period is related to the wavelength of the propagation in this way. So the question is, we have been shown that particles behave as waves, so we need to find a wave equation essentially to describe the physics of particles at the quantum level. Okay, so it has to be analogous to this expression here. Okay, we have to find something like that, and the solution to the wave equation we will call phi of x and t. So we're going to start from assuming there is a solution. This solution here should be equal to something that to these waves associated to a particle. Okay, electrons diffract, so there's a wave associated with the particle. This is the wave associated with the particle. We are interested in finding out what is the equation for that. But let's consider first a free particle. A free particle is a particle that has no potential. It can have a kinetic energy which is equal to p squared over 2m. So written in terms of the de Broglie wavelength, this is when the quantum mechanics starts a bit, meaning we want to write the energy as a function of lambda. Okay, so we said, well, this should be p squared, so it's h. What is the de Broglie wavelength? I didn't write this down. Maybe I should. P is h divided by lambda. So if you have a momentum p, implies that momentum is equal to the Planck constant divided by the wavelength associated to that particle. So I've done this here and replace in this expression h divided by lambda, which is like that. Then what I do next, I multiply and divide by 2p, because this number is going to come up all over the place again. So h divided by 2p squared is h bar squared. That's what the bar shows here. H bar is equal to h divided by 2p. We have discussed that before. And here we have 2 pi divided by lambda. But 2 pi divided by lambda, what is that? That is k squared. So I can write the energy as h squared k squared divided by 2m. In an alternative way, I can say that this energy here, the kinetic energy, is equal to h nu. Now, this is again, this is this is what happened with photons. So I'm saying the energy of a particle relates to the frequency of the particles in a way similar to as photons do. So I'm going to quantize everything in the same way. So this is the kinetic energy is equal to h nu in this case, because h nu is total energy of the particle, because there's no potential in it. Okay. So I write this as h over 2 pi times 2 pi nu. Okay, so the energy, finally I write it as h, this expression here, h nu is equal to h bar omega, okay, which is equivalent. And I have a relationship between omega and k. This is very important here, because now we are at the same level that we were here. We had a relationship between k and omega. Here, k and omega are linear, and here they are not. Omega is linear, and k is square. How do I get the k square in this case? In the case of the particle in one dimension? Well, you know, it has to do with the twice the time derivative of something, of the wave function that I have as a solution. And this is twice the derivative with respect to time. So this could come, if I build an equation, this could come out of a derivative with respect to time, a single one, and this could come as a derivative with respect to space twice. Okay, that's interesting. Look, for a free particle, you know, somehow P, this is the momentum. See, we have just seen the momentum here. P is equal to h bar times k. So this is the momentum. For a free particle, that particle should have a single momentum. So how does it have a single momentum? This is the k, this is the same k. So it will have one momentum for a free particle. It means that I could write a wave, which is a solution for this in the same way. This will have a single momentum and a single energy. Okay, so if this is a solution, I have to find a wave equation that actually provides this relation between omega and k. So this is the puzzle that you know, very talented people at the beginning of the 20th century found themselves when the data from experiment couldn't be explained by Newton mechanics. Okay, so free particles. This is a free particle that travel in the positive x direction with a momentum k and energy. I'm sorry, with a momentum h bar k and an energy equals to h bar omega. Okay. Let's build the equation. So if I have phi, this equation here, and I take a single derivative with respect to position, it brings down an ik. Well, this is the thing. See, that the spatial derivative of an exponential is equal to a times the same exponential. Okay, so that's what I'm doing here. So taking the derivative of this factor and gives me this. Now I take the second derivative and it gives me minus k squared times phi. Okay, well, you know, this thing has a k squared and I had a minus sign in front. If I put a minus sign in front of that, I should make it something like a time derivative of the same phi. Okay, so this is what I do here. I keep this. So the second derivative of phi of that sort of free particle solution is equal to this. Okay, so we have the k squared term. Now we need the omega term. Where do we get the omega term? Well, we take the time derivative of this. We take the derivative of this is simply I omega. Okay, so it gives minus I omega times phi is the time derivative of this. So now there are a few things that I have to fetch here. See, I have to get rid of this I somehow, and I have to get rid of a minus sign. How do I do that? Well, I could say that minus h squared over 2m times the second derivative of the phi dx squared, which is this expression here, is equal to, look at this. This is the energy. This is h squared k squared divided by 2m times phi. I obtained this simply from 3. Here, multiplying by minus h squared over 2m. From 4, from this expression, if I multiply this expression by I times I is minus 1 times minus s, and that minus sign, it gives me a plus sign. So I h bar times the first derivative of the wave function with respect to time provides an expression that is h bar omega over phi x of t. So here I have the thing that should be equal to this. Okay, this is what I know. The de Broglie relationship and the free particle relationship should all be matched together, and this is my initial assumption. If I do that with these two initial assumptions, the only thing that I have to do is to make this part of the equation equal to this part of the equation, and this is what I have done here. Okay. So this is sort of the kinetic energy term, and this is sort of the energy term. This defines that if this is the energy term, it means that the energy is only equal to the kinetic energy of the system, because this is a free particle, so it makes all complete sense. So this is the one-dimensional Schrödinger equation for a free particle. Okay. If you think I am, sort of lying to you here because I haven't actually make a deduction from this equation from something else, it is impossible to do. I don't have a more basic principle to actually do this. What I'm just trying is to motivate that this is a good equation to describe what happens in the microscopic scale. And well, you can get it, even if you don't believe it, you can look at this and say, okay, let's see how it works. What is the capability of making predictions of this equation? And this equation has the most precise prediction of any other equation on Earth, essentially. Okay, so this does not only work, it works very well. Okay, so let me try to convince you of that. And from this very simple argument, the only thing that I did is to get to this equation is this is going to comply with the fact that the de Broglie wavelength is simply equals to h over p, and the energy of a particle is equal to p squared over 2m. Those are the two things that are embedded in here, plus the fact that there is a wave nature to it. Okay, and the solution of this wave nature has to do with what phi means, and I'm going to try to explain a few things. So we can recognize the first term, this term here, as this is what I was mentioning before, gives rise to this term, which is the kinetic energy term. And this term here gives rise to what is called the total energy term. So in the case of the system we are looking at, which is a free particle, the total energy term should be equal to the kinetic energy term. That's the only thing that I'm doing. Okay. The interpretation of this thing is actually requires some work. So I'm gonna try to work that out, sort of the total energy and what does phi mean and what not. This is something that is very relevant here. There's a few things that has to do with language here. Let's get to the interpretation of this thing. The interpretations of what are the variables involved in quantum mechanics. Okay, so I'm going to remind you a bit of of linear algebra here. So if you have a matrix here and you have a B, which is a vector, and you have a multiplication of A times B, that is usually equals to, if that is equal to a number, a value, times the same vector, we're saying here that this equation is the same as solving, let's say you know the matrix and you want to find everything else. You want to find the vector B that actually behaves like this, solves this equation, okay? And you want to find the values that solve this equation. These values here are the eigenvalues of matrix A, and V are the eigenvectors of the same matrix, okay? So eigenvalue in Spanish is valor propio. So we're solving an eigenvalue problem here and finding out what the eigenvectors are and the eigenvalues are. Let me go to the next and let's see how does this look here. Now I'm going to try to interpret, you know, the elements on the Schrödinger, in one-dimensional Schrödinger equation as operators for different quantities. And I'm you know telling you that this thing is an energy operator. Okay, why is it an energy operator? Because I times h bar times the first derivative with respect to time of the wave function is an energy operator, because when it operates over phi, when phi is the free particle energy, it gives the energy h bar omega times phi. And if you look at this equation here, this complete equation, this is the operator. It's not a matrix, it's a linear operator. It's a functional operator, and this is here is the wave function or the eigenvector, and here I have the same eigenvector, and here I have the eigenvalue. So I have the energy operator, the energy eigenvalue, and the eigenfunction. What is this telling us? In the case of the free particle, when I act with the energy operator, I get a single value, which is good, meaning the energy is conserved in the case of a particle moving freely in space. Okay, so for a free particle, the wave function is also an eigenfunction of the momentum operator, you know, because it has a single momentum, nothing is changed. It's a free particle. There are no forces attached to it, so I cannot change the momentum. So it means that if I sort of solve in the same way with an P operator, this is an operator of momentum, acting on phi, it should give me hk times the same wave function. What would be that operator? Well, if I remember well, here I have ik, so if I take the first derivative of this, I drop down an ik, and so I have to multiply by minus I if I want to write the momentum in order to get this. And I also have to multiply by h because the derivatives only brings down a k value. So this operator here, in the same way, this is the energy operator. I can imagine this guy being the momentum operator in the x direction. That's why the derivative is with respect to x. And when I do that, when I act with this expression here, which I call the operator of momentum, I have the eigenfunction, I have here the eigenvalue, and I have here the eigenfunction again. Okay, so this is also a very good thing. When I, for a free particle, the free particle is an eigenfunction of momentum. And where is the momentum? The momentum is actually the thing that I obtain by acting over that wave function by the momentum operator. Well, we have a drama here because now I have this momentum operator here, and I remember I wrote the kinetic energy is equal to pi squared I'm sorry, to p squared over 2m. So I guess I could write an energy operator, a kinetic energy operator, by squaring this thing. What does it mean, squaring? Well, squaring it means applying this thing twice. That's what squaring means. And I have done this here. So the energy operator, the kinetic energy operator, will be the P operator divided by 2m, acting twice. It's squared. So I act one and I act the second time divided by 2m. Well, this thing over here, we know from math that from the regular calculus, of course, that I could write in the same way, minus h squared divided by 2m by the second derivative of with respect to the position. But if you remember well, this is what we got. You know, this is the kinetic energy operator written in this way without the phi there. This is the kinetic energy operator acting on a wave function. Okay, so and now I can reinterpret the meaning of it when I define P as a momentum operator. Okay, so the kinetic energy operator acting on the free particle wave function gives back the energy times the same wave function, and this is what we got. You know, you take the second derivative of it and you get this. Okay. Yeah, everything seems sort of consistent here. We only have one very not minor difficulty, which is the interpretation of what this is. You know, we have a wave function. What the hell does the wave function means? Okay. And you know, people work out on that for a while. And first of all, this is a function, as I have been written it here, and you can see that the actual equation involves things with the complex variable. So the thing is, how do I get to the real thing, the real numbers? The real numbers should be reals at the end. So we have to interpret this wave function in a way that is something real. Okay. So we get to the problem of the wave function, and okay. So we the same as before. No, this warning, I have not said anything about this warning. You read the transparency later and check the warnings. So let's talk about the wave function. So the wave functions are the solution to the free particle wave function is a function that it has a complex value in each point of space. So what does it mean? So this is the question there. So if you were reminded of the experiment that I showed you before, the intensity of the as a function of theta of the electron diffraction experiment, you can see that the intensity somehow has to do with the numbers of points in each point, and when the numbers are higher, this curve is higher, and but when we calculated this in the case of electromagnetic waves, we actually square the value of the electric field, and the square of the electric field has to do with the intensity. And now the intensity, if the thing is more intense, it means that there are more particles in that position. Aha. So we can try to get that back and try to make an analogy here with my wave function of matter and saying, look, maybe if I square to actually follow this interpretation, if I square the wave function, what I have is, and this is a high value, it means that I have a high probability of the particles of being there. And it turns out that is a very good way of thinking, and this was proposed by Max Born at the beginning of the century, of the 20th century, and he indicated us that well, since this thing is complex, in general, we need to square the modulus of this wave function. So the wave function has in there a phase, a shift. And what we are only interested in the case of something that we can measure is the probability of finding a particle somewhere. So our interpretation would be that phi squared instead of phi represent the probability of finding a particle in a certain position. So the equation is probability of finding the particle between x and delta x at the time t. Well, I forgot to put a t, comma t here. P dx and t dx is equal to phi of x and t squared times differential length. Or this is the same as saying that the probability of finding the particle between x and x plus dx at time t is equal to phi conjugated times phi multiplied by dx. You can definitely see immediately what will happen if I'm writing it this way. It means that I could integrate this thing over all the ranges of x, and for a particle, to find the probability of finding the particle in a region of space, I simply have to integrate here in the region of space where I know the wave function, and then I will know the probability of finding a particle there. Okay. Okay, so we have the interpretation of the wave function. We have the interpretation of the operators of momentum. We have an equation for where is my equation? Ooh, here is my equation. My equation for a free particle in one dimension. And my question then is, what about if I put a potential in there? What about it? How do I get now? Let's say I use a confining potential of a certain form as the one that I was showing you before, meaning a particle living inside a box, and I asked you, how do I get that into that equation? Well, we were seeing that the way this thing got in is this is the in the case of the free particle, this is the kinetic energy operator that gives the value of the kinetic energy times the wave function. So the way of getting in a potential energy maybe would be just changing this by the potential energy and multiplying it by the wave function. So that is the 0th order proposition that should be examined. And that means that the energy, the potential energy operator for our equation will be simply multiply the confining potential, or whatever potential it is, VDX. It could be a repulsive potential, an attractive potential. It doesn't have to be a confining potential. Any potential, which is a function of position, multiplied by the wave function. Okay, so this will be the potential energy operator acting on phi. Okay. So this will be the way we could get the potential energy into the equation. And this is what we get. This is the one-dimensional Schrödinger equation for a particle living in a potential VDX. Spectacular. The total energy is IH times the second derivative. This is the kinetic energy term. And this is the potential energy term. Okay. So now this is the equivalent of Newtonian mechanics for the quantum world. Okay. So this is the one-dimensional Schrödinger equation. So this is very relevant in this case, and I think this equation has the as I mentioned to you before, has a prediction capabilities that are, with very high precision. You can guess numbers and measure numbers with absolutely astonishing precision. Okay, so we can have nice predictions based on this equation. We can actually write this equation in 3 dimensions. How do we write it in 3 dimensions? We add up here the derivative with respect to y squared and with respect to z squared, and put them, and we can actually write this thing, which is this differential operator in 3D and cylindrical coordinates or spherical coordinates with r and theta, and actually this will be the way to solve for the equation to find out in using a wave representation of how the hydrogen atom will look like. Actually, the hydrogen atom is the only, it's one of the very few quantum mechanical problems that have been solved mathematically in exact form, because everything else is just very, very cumbersome to have it in a closed form. So it is one of the greatest success of quantum mechanics to do that prediction, and it's used afterwards to actually understand very well how the other atoms, the wave functions of the electrons and other atoms, and explain the periodic table a bit based on is exactly on this equation. Okay, so let me revisit one thing more here, because it's there's a puzzling aspect of this. Is in the case of a free particle, I mentioned, if I take this equation, you all know, because this equation is the solution to this equation when BDX is equal to 0. How do I know that? Because I actually started from the solution to get the equation. Okay, so there's no surprise there. But this equation here is the solution to this. This A here, in general, should be determined by the boundary conditions on each of the problems that we are working out. So we're going to find out. In general, not all the problems can be solved by assuming the free particle solution, because some of them are bound. But you can combine, you can sum free particle solution to actually express the wave function solution of a problem with the potential. Okay, so there's a lot of interesting math aspect coming from this thing that has to be developed, and as you may have already, guessed, that has to do with a lot of with linear algebra in the way that I've showed you before. This the problem of an eigenvalue solution, and we will see that solving this equation is actually finding the eigenvalues and eigenfunctions of an operator, and we are going to come back to this during the next lectures. Before that, before concluding here, let me go back to this one-dimensional free particle. So A is in general a complex constant. The wave function is an eigenvalue of momentum P equals to hk. So for this state, delta Px is equal to 0, because there's no delta of P, because there's only one P. So what happened with delta X? In order for this thing to actually fulfill the uncertainty principle, it means that delta X should be infinity. How come? In terms of probability, I can calculate this probability to be expressed in this way, as phi PDX, which the probability is phi conjugate times phi. If I do that, I get that A conjugate times A is equal to A squared. Okay. And now, as expected, the probability of finding the particle anywhere in space is constant, which is good. It doesn't depend on so it's equally probably of finding it anywhere. So the particle can be anywhere, but I have a problem. The problem that I have is I cannot normalize the integral of PDX dx to 1 with this Because if I know the particle is there, the probability of finding it between minus infinity and plus infinity, if there is a particle there, it should be 1. Okay, the probability of finding is 1. But I cannot do that. I can only say that it's a uniform probability in space. Why not? Because if this is finite, if a squared is finite, and I perform this integral, I cannot get 1. I will get infinity, no matter what I do with the a. Okay. So there's a way of getting around that, and the way of getting around that is, you know, the particle is not really from here to infinity, but it's in a wide region of space. So you're going to be saying, well, let's assume the probability of the particle is going to be 1 to find it between a position 0 and L, and it's going to be 0 everywhere else. If that is the case, I can now say that the wave function for this system is it can be normalized like this. The integral between minus infinity to plus infinity of p dx dx, the dx is missing here, is equal to the integral between 0 and L of this expression, a, which is a constant, times a times dx, which is equal to 1. So my normalizing constant should be 1 over the length of the box. We call it a box, even though if it is 1 dimension, we call it a box. Okay, the length of the box, which makes sense when the length goes to infinity, this thing goes to 0. Okay, so the only thing that I have to do to avoid this infinity problem here is to actually normalize it within a, you know, reasonably large region of space in order to get numbers that make sense. Okay, so this is sort of there was an argument that was hanging before. This is not really the relevant part. The relevant part of what I have, this is the thing here in the orange box, is the relevant aspect of it. Is a summary of this lecture. Okay, and we're gonna take it from here to the next. Okay, so this is it. This is quantum mechanics, guys. Welcome to the world. Okay, this is how it works. Okay, so this is the lecture for today. I don't know, guys, if you have any questions about this.
No, I'm left with no questions at the very least.
Okay. Please, guys, read. Okay, read about this. Ask me things. Stop me. You know, if you don't ask me anything, I'm gonna keep running with this thing. Okay, I'm gonna get to the end of the program. No problem. Have you discussed the thing of how we're gonna grade the last? What is your proposal for our last exam on the course? No proposals. Okay. Okay. We have it scheduled as it is, and we see the shape it takes. Okay. I'm not going to ask you to come to the university anyway to actually do this. We're going to find a way of doing it, which doesn't break all the rules. Okay.
All right, that's perfect.
Yeah. Okay. Okay. So, guys, this is it, and I'll be seeing you on Thursday, and I'm going to try to. I'll promise, solemnly swear that I'm going to do something about your grades, so you have an advance of how far you have been on the course. Okay. Okay, guys. See you soon. Ciao, ciao.
Take care. Goodbye.